Alright guys, today we need to talk about section 2.4. Section 2.4 is all about continuity. Continuity is going to be a very important concept for us throughout the rest of the course. It's kind of nice, it's pretty intuitive as to what the definition of continuity is, what the concept means, but it's going to be very important because continuity is going to be a precondition for a lot of tools that we're going to want to use throughout the rest of the semester. There's going to be a lot of theorems that a prerequisite in order to use that theorem is going to be the function must be continuous, perhaps on a closed interval or maybe an open interval. Okay, so let's hop right in. So what we're going to talk about, three main things. What continuity is at a point and at an open interval, on an open interval. We're also going to talk about one-sided limits, because one-sided limits, we've talked about these informally, but we need to talk about them in a more formal manner to define continuity on a closed interval. Then we're going to talk about properties of continuity, and then we'll work a few examples, look at some graphs in order to determine if graphs are continuous or not. And then there's going to be two different types of discontinuities, problems with continuity that we'll talk about. Okay? Alright, so let's first talk about just what continuity is at a point, then on an interval. So the term continuous, this is kind of nice because continuous means kind of what you think it might mean, as if you can think about continuity, the term continuous, and what graphs look like. So continuous simply means, in an informal way, that a graph is more or less smooth, that it doesn't have any holes in it, any gaps, that it's continuous, it's uninterrupted, I guess would be another way to put that. So it's kind of nice in this sense, because there's a lot of mathematical terms that do not, that don't hold the same definition from just in layman's terms into the math class. Think like, for instance, in stats class, we have a normal distribution. Well, normal doesn't necessarily, just the regular English definition of normal doesn't really give a whole lot of insight into the specific definition of a normal distribution. But here, the normal English definition, dictionary definition of continuous kind of does inform the mathematical definition of continuous. Of course, there's going to be some more specifics to it, but the general idea there is there. Okay, so let's look at a couple examples. Now, these are examples of functions that are not continuous. Okay, here's kind of like the three main problems you might have with continuity. For instance, if you have a function where it has some point that is undefined, okay, there's a hole in the graph. This graph would not be continuous on the open interval from A to B. Now, we're not concerned with the endpoints here. We're only looking at open intervals currently. So we would say this curve is nice and smooth between, say, the open interval from A to C and then the open interval from C to B. But at C, there's a hole in the graph. The function is not defined, so it's not continuous at point C. All right. This one's very obvious because clearly if you look at the open interval from A to B, there's a big gap here. Okay? If you look at, say, the limit from the left here, there's a trend in the y values. The y values are trending towards right where my cursor is. If you look at x values as they approach C from the left. But then if you look at y values as x approaches C from the right, the y values are trending toward right where my cursor is right here. So this is where we have talked about kind of left hand and right hand limits before, but we would say that the limit right here does not exist because the left hand trend in the y values, that is the trend from the left, the y values from the left, don't match the trend from the right. So the limit from the left and the limit from the right as x approaches C don't match, so the limit doesn't exist. Okay, so that's another instance where you will have a discontinuity. So this is not continuous at point C. So we say there is a discontinuity at point C. And here's kind of a third option. It's very similar to the first situation, but here's the third situation where continuity will not be. That's when you have the limit does exist. So here the limit from the left is equal to f of c, and the limit from the right, excuse me, I just said that wrong. The limit from the left is equal to about this y value right here. The limit from the right of c is equal to about the same, or is equal to the same y value, right about where my cursor is. However, f of c is defined down here. Now remember, a limit, the existence of it or not, isn't dependent on the value of f of c. Okay, so like over here, the limit certainly exists. The limit from the left is about this y value where my cursor is, which is the same thing as the limit from the right as x approaches c. And f of c is not defined at all. Over here, f of c is defined, but f of c is defined down here. Now that doesn't affect the value of the limit because the limit deals with the trend in the y values. So f of c is right here, but that's not the trend, so it doesn't affect the limit. But one of the other issues with continuity is that we want the limit to equal f of c as x approaches c. Okay? All right, so here's kind of just the three main situations where we will experience discontinuities. So at each of these examples, there's a discontinuity at x equals c. We'll categorize those discontinuities in just a little bit. Okay? And here's a summary of what we just discussed. The three options where continuity fails to exist. A function is not defined at x equals c. The limit does not exist as x approaches c. And the limit exists, or excuse me, the third option is the limit exists, but f of c is not equal to the limit. You want the limit to equal f of c. Okay? So here is the definition of continuity. Okay, so these were the problems, the things that occur such that continuity fails to exist. Here is what we want to happen in order for continuity to be there. So we want a function to be defined at a point. So this is talking about just continuity at a point C. We need f of c to be defined. We need the limit as x approaches c to exist. And we want these two things to be equal. So this has to exist, and these two things have to be equal. The limit as x approaches c of f of x has to be equal to f of c. If any three of these conditions are not met, then the function is discontinuous at c. But if you can satisfy all of these conditions right here, then a function is continuous at c. Now, what does it mean to be continuous on an open interval? That simply means that every point, the function is continuous at every point. Okay? There's often going to be times where we consider functions that are continuous over the entire real number line, and we'll use the term everywhere continuous for those functions. Examples of those might be your pretty standard polynomial functions, or maybe sine of x or cosine of x. Those are going to be examples of functions that are everywhere continuous because they are continuous at every point in their domains, and their domains are all real numbers from negative infinity to positive infinity. Okay? Now, let's categorize discontinuities. So let's say there is a problem with some particular point in your function. Maybe it's not defined. Maybe the limit does not equal f of that x value, or maybe the limit fails to exist. Now there's two possibilities for the nature of those discontinuities. There's removable or non-removable. Non-removable oftentimes is going to be the result of an asymptote. We'll look at several pictures, not always, but often. But removable discontinuities are essentially when you have a hole in your graph. So let's say you have a function where there's just a particular, usually these are rational functions, and you have a x value for which the function is undefined. Well, typically, if you can just redefine the function such that the function is defined at that value, then that would be what we call a removable discontinuity. If there's no way to redefine the function and essentially plug the hole, like for instance with a vertical asymptote, then the function is said to have a non-removable discontinuity. We'll look at several pictures here, a lot of graphs. It's really important to be graphing these to look at it and visualize what's going on for these type of exercises. Okay, so let's just go back to the three we talked about earlier. Here, this function is undefined at x equals c. However, we could simply say, let the value of f of c equal this y value right here, and essentially we would plug that hole. If we plug that hole, let f be defined at c, then we would have continuity here. We would have a smooth curve because the only problem here was that f of c was undefined. So if we simply define f of c, then we have a continuous curve, thus c is a removable discontinuity. Okay, with graph B here, we're still looking as x approaches c. There is no way to redefine f of c such that we bridge this gap. Now, I oftentimes have students say, well, why don't we just draw a vertical line there? We could draw a vertical line, and then you would have a continuous curve, a smooth curve. But we have to think, what would happen if we drew a vertical line there? If we drew a vertical line there, and so we had like a piecewise definition of this curve, and then we had a vertical line connecting them, a vertical line is not a function, so you can't do that. Now let's say those points were spread apart. We'll have situations where we have exercises where we have functions, a function over here to the left and over here to the right, and we want to connect those functions in order to preserve continuity. But here, there's no way to bridge this gap. And since there's no way to bridge that gap, this is a non-removable discontinuity. We can't get rid of it by simply redefining f of c. Okay? So either for removable discontinuities, you're either going to have an asymptote or you'll have a situation like this. Those are the two main situations you're going to have. The third situation we talked about earlier is this right here, where there is a discontinuity because the limit as x approaches c is not equal to f of c. However, just like with graph A over here, we can simply redefine f of c to equal the limit as x approaches c, and then we will have continuity. So this is a removable discontinuity, but non-removable because there's this gap here that we cannot fix. So if you have a discontinuity, we're typically going to want to categorize the nature of that discontinuity, whether it's removable or non-removable. Okay, so let's look at a few graphs. Okay, let me jot these down real fast, and then I will pull up I'll pull up our graphing program, and we will see what happens here. Let's look at f of x equals 1 over x. Zoom out a little bit. Maybe let's darken this. There we are. Alright, so we should be halfway familiar with this function. We've probably seen f of x equals 1 over x throughout algebra class and pre-calculus. And this is what the function looks like. I know we have talked about in previous classes asymptotes. And x equals 0 is an asymptote here. Now, why is it an asymptote? There is a discontinuity at x equals 0. Now, why is that true? Because for a function to be continuous, it has to be defined at every value, okay, in its domain. Or excuse me, it has to be defined. If we want this to be continuous over the whole real number line, this would need to be defined at x equals 0. However, this function is defined for all real numbers except x equals 0. Now, if you look to the left of 0, we have a smooth curve over here. If you look to the right of 0, we have a smooth curve over here. So we have nice, continuous, smooth curves everywhere except right here, because as you look at the limit, if you look at as the limit as x approaches 0 from the right, the y values are shooting off toward positive infinity. So you look here, the y values aren't so big now, but they are going to get really big really fast, up towards positive infinity. Likewise, as you look at the x values to the left of 0, and you approach 0, getting closer and closer to 0 on the x-axis, look at the y values. They're getting very, very large in a negative way. So they're shooting off down towards negative infinity. So there is an asymptote right here. There's no way to redefine f of x equals something and bridge this gap. For instance, we can't say f of 0 equals 1 and that bridge this gap right here. We can't say f of 0 equals 5 and somehow fix this gap right here. Since that's the case, we say there is a non-removable discontinuity at x equals 0. And this non-removable discontinuity happens to be an asymptote, a vertical asymptote at x equals 0. Again, non-removable discontinuities do not have to be asymptotes, but a lot of times they will be, especially when you're dealing with rational functions. Okay, the next example was one we've actually considered before. It is the rational function x squared minus 1 over x minus 1. Now, you can't really see the problem here because this software is not going to graph or is not going to display by default a undefined point, but we can see here that this function is clearly not defined at x equal 1. And if I kind of hover here, I can verify that point. So it does show, if you hover, it'll show that there's a hole in the graph there, but it's not going to show it by default without hovering. So this function is undefined at x equal 1. So there's a hole there. There's a hole where we would want c comma f of c to be. So by default, or excuse me, just how this function is defined, there is a discontinuity at x equal 1. Because for continuity to exist, the first condition is that f of c has to be defined at that particular x value. So this is defined everywhere except for x equal 1. However, if we consider the limit as x approaches 1, we can clearly see that the limit as x approaches 1 is going to be this y value right here. Now, what do you think that is? Okay, look at the y values. As x is getting closer to 1, the y values are getting really close to 2. And then look as I come down on the right, the y values are getting closer and closer and closer and closer to 2. So the limit here is going to be 2. Now we can verify that algebraically. Now how did we verify that algebraically in past lessons? What we did, we call it evaluating a limit analytically, is we factored the numerator and then divided out any common factors amongst the top and the bottom. Okay. Now if you do that, you can notice that you can factor the top. Let's just go ahead and factor that. It's a difference of two squares, x minus 1 times x plus 1. So that's the exact same graph. It's just factored. And we see clearly here that there is a factor of x minus 1 on the numerator and denominator. So we could divide out those factors, and then we have the new function x plus 1. Okay? That's essentially the process of redefining the function such that f of c is defined. See, these are the exact same function, except g of x is defined at x equal 1. See, there's no undefined there. X equal 1 results in a y value of 2. So I've essentially redefined, x equal 1 to have a y value of 2. So here the limit as x approaches 1 is equal to f of 1, which is exactly what we wanted to happen. So we could simply redefine the y value when x equals 1. We redefine f of c, and so that's a removable discontinuity. Holes are removable discontinuities. So this function is not continuous everywhere. It's continuous on the entire real number line except at x equal 1, but we can fix that discontinuity by a simple redefining of f of c, and thus we have a removable discontinuity at x equals c. So holes result in removable discontinuities. Typically when you have rational functions, the way you can tell it's going to be a removable discontinuity is that it's the factor, it's the problem point that resulted from the factor that you can divide out. So here we divide out essentially that problem point, that discontinuity of x equal 1. It's the one that we essentially got rid of. Those are the removable discontinuities, the ones you can remedy. The non-removable discontinuities are those ones that you cannot remedy. And we'll see some of those. Actually, let's go ahead and look at one real fast. Let's say I have the function, let's see here. Here we go. I want a rational function, x minus, let's say x minus 2 divided by x times x minus 2. Okay? Now, this looks very similar to 1 over x. Okay, in fact, I should redefine this. F of x equals, okay, in fact, this is very similar to the function, let's say g of x equals 1 over x. In fact, see, exact same curve, except this green curve is not defined at x equals 0, and it's not defined at x equal 2. So if I hover here, notice this green curve is not defined at x equals 2. So there are two discontinuities with f of x. There's a discontinuity when x equals 0, because this function is not defined for x equals 0. And there's a discontinuity when x equals 2, because this function is not defined for x equals 0 or x equal 2. Remember, being defined at a particular value of c, that is a precondition for continuity. So this violates the first condition, or excuse me, x equal 2 and x equals 0 both violate the first condition of continuity. So there's a discontinuity x equals 0 and there's a discontinuity x equals 2. Now the question is, how do we categorize those? Now, as we can see here, the discontinuity at x equal 2, that's just a hole in the graph. And essentially, we can redefine f of 2 by simply dividing out common factors and looking at this function right here, which is our way to redefine x equal 2. So at x equal, I just said that wrong. We redefine f of 2. So we redefined f of 2 to equal 1/2. Okay, so the orange function is just like the green function, except that the orange function only has a discontinuity at x equals 0. Thus we say the function f of x has a removable discontinuity at x equal 2. Now, notice here, when we cancel off or divide out that factor of x minus 2, we are still left with this asymptote, this discontinuity at x equals 0. So we've redefined the function at f of 2, however, we're still left with this x on the bottom, on the numerator, so this function is still not defined at x equals 0. There's no way to remedy this situation. There's nothing left to divide, factor, and cancel out. So we're still stuck with this asymptote at x equals 0. In fact, x equals 0, there's the purple asymptote. Okay? Since that's the case, we say that the discontinuity of f at 0 is non-removable, because there's no way to fix that situation by a simple redefinition of f of c. So this function f of x has two discontinuities, x equals 0, x equal 2. X equals 0 is a non-removable discontinuity, whereas x equal 2 is a removable discontinuity. So x equals 0, asymptote, non-removable. X equal 2 is a hole in the graph. That's removable. Okay, let's look at another piecewise function. This piecewise function, now it's a piecewise function. Here's how it's defined. I'm going to define this as kind of separately here, but it's x plus 1, and it's defined for x is less than equal to 0. Okay, so there's the first part of my function. Now I will make sure to put a closed dot there. So that's at, let's see, 0, comma 1, closed dot. Okay, no, I want to make that all the same color here. There we go. Okay, now the other part of my function in this example is e to the x power, the exponential function. Now it's defined over the other part of the real number line, which is x is greater than 0. So x greater than 0. Not greater than or equal to, but greater than 0. Now let's, I guess we can leave that blue. Okay, now let's look here. Now, if you were just looking at the piecewise definition of this, you wouldn't necessarily be able to automatically see whether it's continuous or not, but if you graph it, it'll give you a good idea of whether it's continuous. Now, we know that e to the x power is defined for all real numbers, and the limit exists for all real numbers, and the limit is equal to f of c. As limit as x approaches c is equal to f of c. Now we know that from a previous theorem that was in section 2.3, I believe, the section on analytic limits. It was a properties of limits theorem. Okay. We also know that this function right here, x plus 1, that's a linear function. It's defined for all real numbers, and we can always evaluate those limits by direct substitution. Therefore, f of c is always going to be equal to the limit as x approaches c. So we know in the black line it's completely continuous over the domain x is less than 0, and we know that the blue curve is continuous over its domain. The only thing we're concerned about is what happens at x equals 0. That's like the funny point. What that transition is f of c defined, and is the limit equal to f of c? So let's think about that. Okay, is f of c defined? That's our first condition for continuity. So let's see, is f of 0 defined? Well, yes. This right here is the rule we use when x is equal to 0. So f of 0 is 1. That's the black dot. Okay. The other thing we need to check is to see if the limit exists. Does the trend in the y values from the left equal to the trend in the y values from the right? So as I look at x values, they're getting closer and closer and closer to 0. So my x values are getting closer to 0. What do the y values look like? They're getting bigger, and they're getting bigger, 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 closer to 1. So we would say the limit from the left is equal to 1. Now what about the limit from the right? Okay, I'm going to look at my x values. My x value right now is 1.096, and my y value is 2.992. Watch as my x values get smaller. X values are getting smaller, 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 getting closer to 0. Look at my y values. My y values are also getting smaller, but they're getting really, really close to 1. So my x values are getting close to 0. My y values are getting close to 1. So we would say the limit from the right is also 1. So since that f of c exists, again, f of c is 1. That's the black dot. And the limit also exists, and the limit equals f of c. So f of c is 1. We saw that the limit equals 1. Thus, this function is continuous at 0. So we know it's continuous on the black part, we know it's continuous on the blue part, and we know it's continuous at that point. Thus, this function is continuous everywhere. Okay? So a lot of times the piecewise functions, you need to graph them. And you need to be familiar with graphing these by hand, not just using a graphing calculator, because on some tests you may or may not be able to use a calculator. So make sure you're knowing how to graph piecewise functions by hand, and typically what you want to do is just be checking the point where those piecewise functions connect. Not always, because you might have other points you need to check too, but the main point you want to check is the point where those piecewise functions either connect or where the domains change. So here we're concerned with the domain from x less than equal to 0 and x is greater than 0. So we need to look what happens at x equals 0. Okay? Sometimes you might have a piecewise function defined over 3 different domains. So you might have 2 points to check, or more, depending on how the piecewise function is defined. Sin x, we already saw in a previous lecture that sin x is defined for all real numbers, and the limit exists for all real numbers, and you can find it by direct substitution. So for every x value you can think of, the limit of sin x is f of x. So sin evaluated at that x value. Now that's just for a non-modified sine function. If you start to modify a sine function, it may or may not be continuous everywhere. But for right now, sine of x is continuous everywhere. All right, let's look at some one-sided limits and continuity on a closed interval. Now, we've talked about this many times, limits from the right and limits from the left. Now, we haven't introduced the formal notation yet, but we've spoken about it throughout the semester thus far. So here's how we're going to notate limits from the right. We're going to have the limit as x approaches c, and we're going to put a superscript plus sign on the c. That's going to mean the limit from the right. Limit from the left, we'll call it a left-hand limit. Limit from the left, we put a superscript negative sign on the c. So just make sure we're very familiar with how to write limit from the left and what these notations mean. But we have been talking about the trend in the y values from the left and the trend in the y values from the right. Now this is important because lots of times we will often though deal with functions like this radical function here where it's not defined for all real numbers. Okay? And in fact, whenever you have an even root function, it's not going to be defined for all real numbers. It's usually not going to be defined for all real numbers depending on what's going on. Okay? So in particular, we have the square root of 9 minus x. 9 minus x squared. So if we look at this function, we need to evaluate the limit from the left and the limit from the right. I think I actually made this earlier. Yes. Okay, now, let's see here. So the graph of 9 minus x is this red curve. Excuse me, I keep saying that. 9 minus x squared is this red curve. It's a semicircle. Okay? So 9 minus x squared. Now, let's talk about the limits from the left and the limits from the right. Okay? Now, in particular, let's look at the limit from the right as x approaches negative 3. So negative 3 is the furthest left-hand point in the domain of this function. For instance, we can't look at any value more negative than negative 3. Because if you have any value more negative than negative 3, you won't be able to evaluate that x value because it will result in a complex number, and we're only dealing in real numbers here. So let's consider what's going on here. So let's see how a is moving closer and closer to negative 3 from the right-hand side. And look how f of a, it's the purple line, is getting closer and closer and closer and closer to 0. So we would say there that the limit from the left, that is the trend in the y values from the left, as x approaches negative 3 is 0. Now what about the limit from the left as x approaches positive 3? Okay, as x approaches positive 3 from the left, so a is getting closer and closer and closer to positive 3. look at what's happening to the y values, f of a, that purple line. They're getting smaller, 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 and finally they are going towards 0 as we get really close there. So we would say the trend in the y values, that is the limit as you approach positive 3 from the left, is going toward 0. So that's the idea. Again, we've talked about this on many occasions of left-hand limit and right-hand limit, because it makes no sense to talk about the limit from the left, the limit from the left as x approaches negative 3, because there are no x values over here. There is no function over here. Likewise, it really makes no sense to talk about a right-hand limit around the point x equals 3, because there is no function over here. Thus, we only talk about a left-hand limit to this endpoint, and we only talk about a right-hand limit over here, because over here a left-hand limit makes no sense. So we only talk about a right-hand limit. So in general, the two-sided limit does not exist here, because the left-hand limit doesn't exist at all. But a one-sided limit does exist. So this is why that concept is important, because there will be times where a left-hand limit doesn't exist, like here, but the right-hand limit does. In an analogous sense, over here, the left-hand limit exists, but there is no function over here on the right, so the right-hand limit does not exist. Like if I look at f of 3.5, somewhere right here where the cursor is, f of 3.5 doesn't exist. So talking about a trend in the y values over here makes no sense, because there are no y values for these x values that are greater than 3. So that's the idea of a left hand versus a right hand limit. Okay? So again, we've evaluated this at the left and at the right. Let's look at one-sided limits for the greatest integer function. It's also oftentimes called the floor function. Now, you might not have seen this symbol before, but here's how it's defined. To evaluate this function, you simply assign the greatest integer. Okay, so you plug in an x value. You return the greatest integer such that that integer is less than x. Now here's what the graph looks like. Let's see here. I think I have it saved. Yes, greatest integer function. Here's what the graph looks like. Now let's turn off that blue line, turn off green, and there you go. Okay, so this red graph here is what the function looks like. Okay, ignore the green point and f of a for the time being. That'll make more sense in just a sec. Okay, so let's say you want to evaluate, and again this is called the floor function, you want to evaluate f of 1/2. Well, the y value that's assigned to to 1/2 is the greatest integer less than 1/2. But what's the greatest integer less than 1/2? It's 0. Now remember, what are integers? Integers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so forth and so on. And they're additive inverses. So -1, -2, -3, -4, -5. So 0, whole numbers, and all their negatives. So if you want to evaluate, say, f of 1.58, 1.59, well, the greatest integer less than 1.59 is 1. The greatest integer less than all of these numbers where the cursor is 1. Notice these are all decimal numbers between 1 and 2. And the greatest integer less than all those numbers is 1. Now what happens at this value? Okay, well, at f of 2, the greatest integer less than or equal to 2 is 2. So this function has an open dot here, but a closed dot there, because in order for it to be a function, it has to pass the vertical line test. So these 2 can't be f of 2. F of 2 is defined here because the greatest integer less than or equal to 2 is 2. Okay, so this is what the graph looks like. You're going to have open dots here, closed dots here. Now let's look at a limit. So let's turn this back on, this back on. Okay. Now let's look at the trend in the. Let's look at as x approaches 1. Okay. Actually, let's look at x approaches 2. Okay. So there's you can see everything a little bit better. As x approaches 2. Okay. From the left, what's the trend in the y values? So right here, the trend in the y values from the left, okay, getting closer and closer to 2. The trend in the y values is simply the constant. It's the constant 1. See how that blue line is not moving? The trend in the y values, they're all the same on this interval. They're all at 1. Now, that's the limit from the left, we would say, is 1 as x approaches 2. What about the limit of f of x as x approaches 2 from the right? So we looked at the left-hand limit over here. As x approaches 2 from the left, the limit is 1. But as x approaches 2 from the right, the limit's 2. So there again we have the idea of a left-hand limit versus right-hand limit. Now, we would certainly say that the two-sided limit does not exist, because for a two-sided limit to exist here at x equal 2, the left-hand limit has to equal the right-hand limit. So the two one-sided limits are not the same. Thus, the general limit does not exist, but those two individual one-sided limits do exist. And that's going to happen actually at every integer x value. That's going to happen at 0, that's going to happen at 1, at 2, at 3, at 4, at -1, at -2, at -3, so forth and so on. That same scenario is going to play out at each integer x value. Okay. Now, let's look at some more examples here. So that's what I just mentioned here. We have the two-sided limits, okay? The limit from the left and the limit from the right. Okay? They have to equal the same number if the two-sided limit exists. So be very clear with what this notation says. It says let f be a function and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if the limit from the left equals L and the limit from the right equals L. So that means the limit from the left and the limit from the right have to be the same thing for the general two-sided limit to exist. Now, we're not always going to say two-sided limit. Usually we just refer to the limit where it doesn't say left or right. That just means by default the two-sided limit. So if you hear me say, or the textbook or a test or homework say, find the limit, that means two-sided limit. But if it says one of these two notations, then we're specifically talking about a one-sided limit. But if you don't see either of those two subscripts, then we're just looking for the regular general limit, which is two-sided. Okay, so just be careful with that notation. Okay, now, why do we do this in this section specifically? Because we need to talk about continuity on a closed interval. So just like I was talking about, there's going to be theorems in the future where continuity is a prerequisite. Sometimes continuity on an open interval is a prerequisite. Other times, continuity on a closed interval is a prerequisite. So here's how we test for continuity on a closed interval. It's really barely harder than testing for continuity on an open interval. The only extra things you have to do, so after you verify a function is continuous on the open interval from a to b, all you have to do is to verify that the limit as x approaches your left-hand endpoint, in this case a, the limit as x approaches a from the right is equal to f of a. So you want to ensure that the limit as x approaches a is the y value, the limit is this point right here, not some other point. So let's say that f of a was defined down here where my cursor is, then that function would not be continuous on the closed interval. And you want to do an analogous method for the other endpoint b. you want to look at the left-hand limit as x approaches b and verify that that equals f of b. This is really easy to take care of. It's not hard at all. Okay? So let's see here. Let's go back to that function we talked about earlier. So we know this was the semicircle where it had a radius of 3, and it was defined. It was like a semicircle in the upper two quadrants. Okay, so we know that the domain here is -3 to +3. So we want to check to make sure that this is continuous on the closed interval. So we want to check to make sure this is continuous on the closed interval. Now, all we need to do in order to show that is that the limit as x approaches 3 is equal to f of 3. Now, what's f of 3? Okay, remember our function is the square root of 9 minus x squared. So as x equals 3, 3 squared is 9, the square root of 9 minus 9 is 0. So f of 3 is 0. All we need to do is verify that the limit as x approaches 3 from the left is also 0. And that's exactly what we talked about earlier. This limit as x approaches 3 from the left is indeed 0. We also need to verify that the limit as x approaches -3 from the right is equal to f of -3. Now, what's f of -3 here? Well, by looking at the graph, f of -3 looks to me like it's going to be 0. Let's verify that algebraically. Remember, f is defined as the square root of 9 minus x squared. If x is -3, -3 squared is +9. We would have 9 minus 9, the square root of that, so square root of 0. So f of -3 is 0. So we want to ensure that the limit as x approaches -3 from the right is also 0. And as we talked about earlier, that limit is indeed 0. So we have just verified that this function right here is continuous on the closed interval from -3 to +3. It's continuous on the interior because we can plug in any x value greater than -3 but less than +3, and we can evaluate that limit via direct substitution. So it is clearly continuous. There's no holes anywhere on this curve on the interior. And then we check the two endpoints to make sure that the right-hand limit over here equaled f of -3, and the left-hand limit over here equaled f of +3, since in both cases the limit matched f of 3 and -3, that was all we needed to do extra to verify that this function was continuous on the closed interval. Okay, so all we did there was check the endpoints. That's all we had to do. Now, how could I break this? How could I break this? I could break this by simply doing this. Let's say 3, 0 is, let's first all make it red. Let's make it open. So let's say f of 3 is not 0. Let's say f of 3 is 3, like that. Okay, and I'll label that as 3, 3, I'll call it 3, and then f of 3. Okay? So, now let's say that is the situation we're dealing with. Okay, well, still, over here, the limit from the right as x approaches -3 is still equal to f of -3. But over here, the limit is unchanged. The left-hand limit is still approaching 0 as x approaches 3 from the left. But what is f of 3? F of 3 is 3. Okay, that's just because I defined it that way. Has nothing to do with this curve x, the square root of 9 minus x squared. I just defined it haphazardly up here. But as this is defined, the limit as x approaches 3 from the left is not equal to f of 3. because f of 3 is 3. The limit as x approaches 3 from the left is 0. 0 is not equal to 3. So if this function it was defined as I have it as it stands right now, this would not be continuous on the closed interval because I broke it, because I redefined the f of 3 up here when the limit is 0. So that would be a situation where continuity on the closed interval would not occur because f of 3, that is f of the right-hand endpoint, is not equal to the left-hand limit as x approaches that right-hand endpoint. Properties of continuity. So these are properties of limits that we should have memorized at this point. So essentially, we can say that point 2 here, we can say that the limit of a sum is the sum of a limit, or the limit of a product is the product of the limits, or the limit of a quotient is the quotient of the limits, provided the denominator is not 0. Okay, these should be very well memorized at this point. Now we have a few more to add to our list, and these deal with continuity. These say that if you have two functions, f and g, and they're continuous at c, then f plus g is continuous at c. F minus g is continuous at c. F times g, or f divided by g are all continuous at c. Or let's say b is just some scalar multiple, some real number. If you take a continuous function at some point x equals c, and then multiply that function by just a non-zero number, or actually not non-zero, any real number, then that is also a continuous function. So we can combine functions in different ways, and as long as the original functions are continuous, then the new functions will be continuous. But be careful of the quotient and the denominator being 0 there. Okay, so let's think about this. Polynomials are continuous. We've talked about it on many occasions. Because polynomials, you're just adding or subtracting or multiplying by scalar multiples. So you have things like x squared, maybe times a coefficient, and then you add other multiples of x and powers to it. Those are all continuous, and you're adding or subtracting them, and so that's still a continuous function. Rational functions are continuous as long as the top is continuous and the bottom is continuous, and of course the bottom's not equal to 0 at a certain point. Okay? Radicals are continuous on their domains. Trig functions are continuous on their domains. Exponential, logarithmic. Now, clearly, tangent x, cotangent x, secant, and cosecant are not continuous everywhere, because if you remember from these four functions and their graphs, they have asymptotes. But sine and cosine are continuous everywhere because they do not have asymptotes. They are nice, smooth curves. They're defined for all real numbers. So these functions are continuous at every point in their domains, but just realize some of these functions have domains that are not all real numbers. For instance, radicals, if n is an even root, are not going to have domains that are all real numbers. Now, if n is odd, so if n is, say, 3, then the domain would be all real numbers. And I should put the caveat in here. If these functions, if sine x is not modified heavily. Now, you could have some composition going on involving sine functions that's not continuous. For instance, in a few minutes, we'll look at sine of 1 over x. Sine of 1 over x is not continuous over the real number line because of that 1 over x as the argument. But we'll look at that in a few minutes. Okay, so with composite functions, if f and g are continuous at a point, then f composed at g is continuous at that point. So that means we could look at, say, this composition right here. Okay, the square root of x is continuous on its domain. X squared plus 1 is continuous on its domain. And so if we're looking at a a value of x that's in the domain of both of those functions, and we compose them, then that result is also continuous at that particular x value. Okay? Let's look at a few examples here. We're almost done. Let's see here. We're going to test for continuity, and this is going to be by graphing. Okay? Now, if I want to look at the intervals on which tangent is continuous, clearly tangent has asymptotes. It's not defined for all real numbers. You can either think about the rectangular coordinate graph, the Cartesian coordinate graph, or think about your unit circle and think about the points where tangent is not defined. In fact, let's just pull up the graph. Let's say here, let's look at a new graph and just say y equals tan x. Okay? Now, let's do this where it's pi over 2. Okay, so there we go. This is the graph of tangent x. Now, where do all those asymptotes occur? They occur at the odd integer multiples of pi over 2. I'll put a few asymptotes in there. X equal pi over 2. X equal negative pi over 2. X equal 3 pi over 2. Let's see, x equal negative 3 pi over 2. So those are, just a few. Oh, I didn't do that right. Negative 3 pi over 2. So there's a couple of the asymptotes. But again, those asymptotes occur at every odd integer multiple of pi over 2. Negative and positive, of course. So tangent of x, otherwise, though, is continuous. So let's say here, from negative pi over 2 to pi over 2, tangent is continuous. There's a discontinuity at pi over 2, at 3 pi over 2, at 5 pi over 2, at 7 pi over 2, at 9 pi over 2, at negative pi over 2, at negative 3 pi over 2, at negative 5 pi over 2. Those are all discontinuities. But otherwise, tangent is continuous. So if we wanted to discuss the continuity of this function, we would say something to the extent of tangent of x has discontinuities at odd integer multiples of pi over 2. Therefore, tangent is continuous otherwise. So tangent would be continuous on the open interval from negative pi over 2 to pi over 2, from negative pi over 2 to 3 pi over 2, that is the open interval, and so forth. Okay? We would also say we want to classify those discontinuities. Since these are asymptotes, they are non-removable discontinuities. Another way to think about this is, what is tangent x equal to? Tangent of x, we could also say, is the exact same thing as, let's see here, sine x divided by cosine x. Okay? Same exact thing. Where is cosine 0? Think about your unit circle. Cosine of 0 cosine of x is equal to 0 at pi over 2, at 3 pi over 2, at negative 3 pi over 2, at negative pi over 2, so forth and so on. So you can think about tangent as sine over cosine and also reach the exact same conclusion. Okay? All right. Let's look at this piecewise function here. Sine of 1 over x for x is not equal to 0, but if sine is equal to 0, redefine f of x as 0. Okay, so let's see here. New graph. So sine of 1 over x. Okay, we talked about this earlier in the class. We said that the limit as x approaches 0 does not exist. Now, that is because this function right here is oscillating very, very, very quickly between negative 1 and 1. And the closer you get to 0, the faster it's oscillating. Okay? So in fact, if you pick any positive number, or any number close to 0, let's say negative or positive, if you pick any number that's close to 0, no matter how small, that function will oscillate an infinite number of times between 0 and that number. Thus, there is no trend in the y values, so the limit doesn't exist. Now, we could say x, actually, let's just not worry about that. And let's just say, okay, let's fix the problem. And clearly, f of 0 does not exist here. Okay? So what we want to do here is figure out what happens at 0. Because this is continuous, except, this is a nice curve here. The oscillations are fine, except at x equals 0, in order for us to have a continuous function, the limit has to exist. So the limit exists everywhere except for at x equals 0 because of the denominator right here. But if we attempt to fix that situation by saying, okay, well, let's just let f of 0 equals 0. So we can't plug in a 0 into sine of 1 over x. So let's just say, all right, well, let's just plug the hole and put a 0 there. Okay? You would think that might fix the situation, kind of like a removable discontinuity type thing. But in order, or excuse me, the other part of continuity is that the limit has to exist. And the limit as x approaches 0 does not exist. So even though we attempted to patch the hole here to fix the problem at x equals 0, we can't because the limit does not exist. Even though we plugged in 0, 0 and redefined f of 0 because f of 0 is not defined here. So we would say at x equals 0, there is a non-removable discontinuity. Otherwise, though, this function is continuous. So it's continuous from negative infinity to 0, the open interval, and then the open interval from 0 to positive infinity. At x equals 0, there's a non-removable discontinuity. Okay? We talked about this during class. This is an interesting example. If you look at the exact same situation, except you put a factor of x out front. So all you gotta do is this. Okay? That changes the situation a little bit. Now here's what I want you to know, or what I want you to see. Okay? Look at the trend here in the y values. The trend in the y values as you get really close to 0 looks like they're going towards 0. Looks like they're going towards 0. I mean, it's still oscillating, but the trend there looks really defined. Now, here's kind of like a cool little application of the squeeze theorem. Let's look at y equals absolute value of x. Nope, x. Look at that. It matches up perfectly. What about y equals negative absolute value of x? I'll make that green as well. Actually, I'll make it blue, so you can see it a little better. Okay? Look at that. Now, what does the squeeze theorem tell us? The squeeze theorem tells us that if you can bound a function, in this case, I want to bound this function right here, the red function. If I can bound it from above and below, and look at the limit of each of those boundaries, of each of those bounds, sorry. Look at the limit as x approaches 0 here. Look at the limit as x approaches 0 here. And if those two limits are equal, then the limit in the middle has to also be that number. So, if you look at the limit as x approaches 0 of the green absolute value function, the limit is 0. The y values are both getting towards 0. From the right, they are going towards 0. From the left, the y values are getting towards 0. Look at the blue lines, the blue absolute value function. Look at the x values. X values are getting really close to 0. Y values are getting really close to 0. From the right, as x gets close to 0, y gets close to 0. So the limit from the left and the right, so the two-sided limit of each of these functions is equal to 0. And since we can write this inequality, let me see here, I'll write this out for you since I'm just talking. We can say that if we define this as f of x, just for some notation here, so that's f of x. If we can say, or we can say that the absolute value of x the negative absolute value of x, is less than or equal to f of x, which is less than or equal to absolute value of x. We can write that inequality. We know that this limit as x approaches 0 is 0. We know this limit as x approaches 0 is 0. Thus, the squeeze theorem tells us that the limit of f of x as x approaches 0 is also 0. Now, this is fundamentally different than the previous example, although related, very different, because the limit of f of x as x approaches 0 we just showed is equal to 0. So we redefine f of 0 to be 0, and now we have met our properties of continuity. F of 0 exists, that is, f of 0 is equal to 0. And the limit, it also exists, we just showed the limit exists, and the limit equals f of 0. So this function right here is continuous over the entire real number line. It's piecewise defined. It's defined as this x sine of 1 over x for x not equal to 0, but for x equal to 0, f is 0. Now, last thing I want to do real fast is just classify non-removable or removable discontinuities and find those continuities, discontinuities. So, let's consider this function x, f of x equals x over 6, I can't talk. F of x equals 6 over x squared minus 4. Now, what would you think? Let's just think about this without even graphing it for the time being. What are the x values that make the denominator 0? X equals 2 and x equals negative 2 make that denominator 0. Okay? Is there any way to factor the top and the bottom and divide out any factors? Well, we could certainly factor the top. We could list 6 in its prime factorization. We could factor the bottom, but we can't divide anything out at that point. So those 2 points that make the denominator 0 are going to be non-removable discontinuities. Now, typically in an irrational function, if you have a non-removable discontinuity, it's going to be an asymptote. And I think it's going to be, we're pretty safe assuming that's going to happen here. 6 divided by x squared minus 4. Okay, zoom out a little bit. And yeah, I think we do have 2 asymptotes. Now, what did we say our discontinuities were? We said they were x equals 2, looks like an asymptote, and x equal negative 2 is an asymptote. Again, there's no way to bridge these divides right here. Okay, there's a big gap here, no way to fix it, because right here the red curve is going down toward negative infinity. All right, here as x approaches 2 from the right, the y values are going towards positive infinity. Now let's talk about some of these limits right here. Okay, we would say the right hand limit as x approaches 2 is positive infinity. Now I'm a little bit ahead of myself talking about infinite limits. That's for section 2.5, but here's a preview of section 2.5. The limit as x approaches 2, the two-sided limit, doesn't exist. We talked about that earlier in the semester. The limit, the two-sided limit, as x approaches negative 2, does not exist. That's because there's unbounded behavior. However, we will introduce this new concept of an infinite limit. That is, the limit as x approaches 2 from the right, the y values are getting bigger and bigger and bigger. They're unbounded. So we would say the limit is equal to positive infinity. Now, I want to be clear here. When we say the limit as x approaches 2 from the right is positive infinity, that is just a special way to say the limit does not exist, and the reason the limit does not exist is because of unbounded behavior. So just because we say equals infinity does not mean the limit exists. The limit still does not exist, so it would be like a DNE answer, but since it's going towards positive infinity, we're just introducing a new way to talk about a limit not existing. Now, the two-sided limit as x approaches 2 does not exist at all, because left-hand limit does not equal right-hand limit. But the one-sided limit is going towards positive infinity, so we say equals positive infinity. The limit from the left, as x approaches 2, those y values are going towards negative infinity. So we would say the left-hand limit is equal to negative infinity. The two-sided limit does not exist, but the left-hand limit does not exist. And we say, but the way we write that is equals negative infinity. The right-hand limit does not exist, but the way we write that, at least according to our textbook, is equals positive infinity. Same thing happens over here at negative 2. As x approaches negative 2 from the left, the y values are getting bigger and bigger and bigger. They're unbounded. So we would say the left-hand limit of x equals negative 2, the left-hand limit of f of x as x approaches negative 2 is equal to positive infinity. Again, that's just a special way to say it doesn't exist due to unbounded behavior. The limit from the right as x approaches negative 2, those y values are going towards negative infinity. So we would say that left-hand limit equals negative infinity. Again, doesn't exist, but we say equals negative infinity. Just a special way to say it does not exist. The two-sided limit does not exist at all because the left-hand limit does not equal the right-hand limit. Okay? So again, that's a little bit of a preview of section 2.5, where we're headed next. The next example was x minus 2 over x squared minus 4. Okay? So let's look at a new graph here. X minus 2 divided by x squared minus 4. This is actually very similar to an example we looked at earlier in the lesson. So we know that looking at the denominator here, that 2 and negative 2 make the denominator 0. Thus 2 and negative 2 are not in the domain of, if we call this f of x, are not in the domain of f of x. Okay? Thus 2 and negative 2 are discontinuities. Now, looking at the graph here, let's just say we didn't have the graph. How would you figure this out algebraically? Well, we know that there's two discontinuities. The way we would determine this algebraically is to factor the bottom and then see which factor we can cancel out. So we could say this is x minus 2 times x plus 2. Now, which factor can we cancel out? Okay, we can cancel out the x minus 2 factor. That means that the discontinuity that was a result of that factor is removable. Well, what discontinuity was the result of that factor? Now, this is where a lot of students get confused. The discontinuity as a result of this factor is positive 2. Okay? Positive 2, that discontinuity, that hole right there, that's the result of the denominator factor x minus 2. But when we cancel that off, when we divide it off, we're left with the expression 1 divided by x plus 2, which is the exact same curve, but it's defined at x equal positive 2. Now, I said exact same. It's exactly the same except for that one discontinuity. Okay? So 2 is a removable discontinuity. It's a hole. We can plug that hole by rewriting the function or by simply saying, all right, let's let f of 2 equal whatever it needs to equal. Okay? 1 over 4. Okay? But when we rewrite that function, 1 divided by x plus 2, this discontinuity that's a result of x plus 2 is still there. We can't get rid of that. Now, what discontinuity is resulting of the x plus 2 factor? It's the x value that makes that denominator 0. So negative 2 is the discontinuity that results from this factor. So just be careful with, it's kind of like an opposite, it's counterintuitive, it's from what you might think. But just remember on like what you would be doing. You would be solving this little mini equation equal to 0. So the solution to x plus 2 equals 0 is negative 2. Okay, so the discontinuity that's a result of this factor that we can't get rid of is negative 2. So that's the non-removable discontinuity. That's the vertical asymptote. Okay, so you could determine that completely algebraically without even looking at the graph. Okay, because the factor that you cancel out, those discontinuities are removable. The ones that you're left with are the non-removable discontinuities. But just it's good to graph these, because sometimes I have a lot of students that kind of mix up the -2 and +2, which one's removable and which one's non-removable. But again, just be careful. Just go, draw yourself a graph, do a sketch, and I think you'll be able to tell which one is removable versus non-removable. Okay. All right, almost done here for the day. Let's look at 2 piecewise, and then we'll call it a day. Now, with these, it says, let's see, do the functions have any discontinuities? If so, are they removable or not? All right, so we know that this linear function here is defined for all real numbers. It's continuous. Now, we're only considering that over this, this domain. We also know that x squared is continuous. In fact, we know that each one of these parts is continuous. Now, what we don't know is what happens at x equal 1. Okay, so we need to graph these to see what happens at x equal 1, because they might not be connected. There might be a gap between these 2 functions. But let's just see. All right, so we have f of x is defined piecewise. It is -2x plus 3, but that's only over the domain x is less than 1. So there's the first part of my piecewise function. Now the other part is x squared, but that's defined for all other x values, x greater than equal to 1. Okay? Now, I should say that x greater than equal to 1. Okay, so we're going to use f of x equals x squared to evaluate f of 1. Now, the only point we were concerned about was what happens at x equal 1. So we need to verify that this function is continuous at x equal 1. Now, there's 3 conditions. Because we know the red curve is continuous to the left. We know the orange curve is continuous to the right. We're only not sure about what happens at x equals 1. So there's 3 conditions to verify continuity. First of all, f of c has to be defined. So c here is 1. So is f of 1 defined? Yes. We use x squared to evaluate f of 1. So f of 1 is equal to 1. Okay, so that's good to go. We verified step 1. Okay, so let me write that down. Okay, step 1, f of 1 is defined. Okay, what about step 2? Step 2 is, does the limit exist? Now, for the limit to exist, as x approaches 1, the left-hand trend has to equal the right-hand trend. What do you think? Okay, if we look at the y values, as x is getting closer and closer to 1, the y values are getting also closer and closer to 1. So we would say the right-hand limit equals 1. What about the left-hand limit? Okay, x values are getting closer and closer to 1 from the left. The y values are also getting closer and closer and closer to 1. So we would say the left-hand limit equals 1 and the right-hand limit equals 1. Thus, the limit exists. Okay? Now, the third condition we want to check for continuity is, does the limit equal f of c? And I think here it does clearly. We said f of c was 1. We said the limit is 1. So the third step was just to verify the limit as x approaches c is equal to f of c, which are both 1 in this case. Okay? So we have verified these 3 conditions, so continuity at x equal 1 exists. So this function is continuous at x equal 1. We know it's continuous because to the left, because that's a linear function. We know it's continuous to the right because that's a polynomial function, quadratic. The only thing we were concerned with is what happens at x equal 1, and that function is continuous everywhere since it's continuous at x equal 1. Okay? Now, that's how you need to solve these piecewise functions. You pretty much have to graph them. Now, I'm using a software package right now to do this by hand. You just need to go slowly and make sure to make a nice graph. That's all you gotta do. I have actually put out 2 examples on YouTube earlier this week on how to graph these by hand. Again, not hard. Piecewise makes a lot of people nervous, but it's not hard to graph as long as you understand that you're just graphing different functions over different domains. Now, the other example was negative 2x, and that was over the domain x is less than equal to 2. Okay, so there is that function, and we should put a point here to stress that at 2, negative 4, we're going to use that function to evaluate f of 2. Okay? So there is half of my piecewise function. Now what's the other half? The other half was x squared minus 4x, plus 1. Oh, plus 1. Nope. There we go, plus 1. Now that was defined for all the other x values. So x is greater than 2. Okay? And just to stress the point here, that if we look at f of 2 is down here, not here. I'm going to say, let's see, that is 2 comma negative 3. Let's make it green to match. And that is an open dot. So we're not about, f of 2 is not negative 3, f of 2 is negative 4, as per our directions in the piecewise definition. Now, I think we can clearly see that there's a discontinuity here at x equals 2. Okay, there's a jump in the graph. These aren't connected. That's kind of like the informal definition of a discontinuity. There's a hole there, or the graph is not connected. There's a jump, something like that. Okay, and so there is a jump here, and since we cannot bridge the jump, there's no way to bridge these without using a vertical line. We can't use a vertical line because that's not a function. So we can't easily redefine f of 2 to make this a function, because we could redefine f of 2 as negative 3, but then that still wouldn't bridge the gap. So this, we would say 2 is a discontinuity, and it's a non-removable discontinuity. So again, non-removable discontinuities don't have to be asymptotes, and usually when we have these piecewise defined functions, they're not going to be asymptotes. They're going to be these jumps in the graph. So we would say to the left of x equal 2, the function is continuous, and to the right of x equal 2, the function is continuous, but at x equal 2, the function is not continuous. Specifically here, the limit from the left is not equal to the limit from the right. Okay, so going back to our 3 conditions, f of 2 is defined. That's the first condition. But the second condition is the limit has to exist at x equal 2. The limit from the left, let's look here. Look at the y values. The y values are getting closer and closer and closer to negative 3. So the limit from the left is equal to negative 3. The limit from the right, the y values, so x values are getting closer to 2, y values are getting closer to negative 4. So the limit from the left is negative 4, the limit from the right is negative 3. Since the left-hand limit does not equal the right-hand limit, the general two-sided limit does not exist. So that's the condition here of continuity that's violated. The limit does not exist. And clearly, if the limit does not exist, we can't even talk about the third condition, which is the limit equaling f of 2 in this case. So if the limit existed, the limit would need to equal negative 4, but the limit doesn't exist, so we don't even need to continue to checking that third condition, because a discontinuity here exists at x equals 2. Anything less here to talk about? I actually did one of these examples already earlier this week, so you can check out my other tutorial to show you how to work a problem like this. Essentially, is we want to find a linear function here such that the entire function f of x is continuous. So we have this definition. We use this constant function for x values less than or equal to -2. We use -6 to define our function for x values greater than or equal to 4. And the question is, what do we need to put in the middle such that the entire thing is continuous? And specifically here, it's asking what linear function, because there could be quadratics or all kinds of things that could work. But to make things simple, it's asking for the linear function that makes this work. Okay? And I actually did a very similar example to this, so you guys can refer to that other example if you want to see how that's worked. Again, I've assigned a couple problems, or at least one problem in your homework that looks like this. So if you guys have any questions, let me know. Hope this has been helpful. You guys have a nice weekend, and we'll see you next week.